Say that I'm doing some research and I have a question. In this case, say I want to know the book Rabbit Run was written by which author. The first thing I'd probably do is ask an LLM. This includes large language models and providers such as ChatGPT, Gemini, and Claude. The LLM will probably immediately tell me that the answer is John Updike. But what actually goes on in this middle step here in between the origin of my question and getting the answer? In this video, we'll go through a high-level overview of how an LLM architecture works and what actually happens in this middle step, following our input through the LLM all the way to its output answer. If we zoom into a high-level view of one of these LLMs, we can see that things are really broken up into three components. A pre-processing stage where the data is prepared and transformed from text to numerical vectors that the LLM can understand. A primary processing stage where the model interprets the input and forms an internal representation of its meaning. And finally, a post-processing stage where the model prepares its output for the user back from vectors to text. We can map this high-level overview directly to the LLM architecture. We can see on the left-hand side, given a textual input, the query goes through many steps and phases before we get our final output. We first tokenize our text, then incorporate token and positional embeddings. We run the corresponding embedded vectors through n-many transformer blocks, and finally through an output layer before getting our final answer. Of course, most of this probably doesn't make much sense to you right now, but let's dive deeper and explain simply what all of this means on a high level. We can again split up our overarching architecture into three primary components: an input representation stage, primary processing stage, and finally an output stage. Let's first focus on the input stage. Please note that in this video I'll use words in place of tokens to make explanations easier to understand, but rest assured we will go through tokenization in complete detail on the next video in this series. So to begin, we must first convert our raw textual input into a numerical representation which our LLM will understand. This means converting our written text into a set of vectors. And each of the vectors that we see here, which we derive from our text, is a representation of one word in our input text. Each one of these embedded vectors carries information on what each respective word is and where it is in the sentence. So for example, our vector for book includes both its meaning and position, where the meaning is the identity of the word, i.e. here that it's a noun and object, and its position, wherein here the location of the word in the sequence is 2. We then pass these embedded vectors from our first stage to a secondary processing stage. In this stage, we take our input vectors and process them through our transformer blocks. I've included one here for this representation, but there are usually n-many of them. From these transformer blocks, we then get as output context-aware vectors. More specifically, these transformer blocks take each isolated input vector from our first stage and enrich them with information from the rest of the sequence. Let's consider a sequence of words in our input, and let's specifically focus on the word book. We got from our first stage an embedded vector representation of this word, which encapsulates its meaning and position within the sequence. However, what this vector does not contain is any information regarding any of the other words in the sequence. That is, this vector representation of book does not contain any information regarding its context, dependencies, relevance, nuance, or intent. All of these things are crucial when a human reads and understands a sentence. For example, knowing the context surrounding the word book in this sequence lets the model know that this isn't a book in general, but that it belongs to a specific phrase, where without Rabbit Run, the model would not know which book the question refers to. Dependencies, on the other hand, tell the model how book relates grammatically to other words, where in this case book depends on written, meaning a book is the thing that was written. And as such, the model needs this to link book to author. Relevance tells the model what matters most for answering the question. For instance, the word book here is more important to the answer than the words the or was. The model must understand that the identity of the book is central to finding the author. Finally, the intent tells the model what the sentence is doing, and iterations capture how two words influence each other's meaning. In short, we want to know how much attention to show other words within the sequence in relation to our keyword. So when considering the word book, which, written, and author are the most important. This information allows the model to answer questions with respect to the input, such as which book, what is the question asking for, and what type of answer is expected. To incorporate this information, we inject the representation of a given word with contextual information from the other words in the sequence. So we take our input vector for the word and process it through our transformer block to bake in this information and provide us an updated vector representation that encapsulates this contextual data, which is why we call our output vectors contextualized vector representations. We then do this for each word in our sequence, injecting relevant contextual information from other words to give us an updated vector representation. As such, we exit our transformer block with an updated set of context-aware vectors. We then enter our final stage, which is the output stage, where we take our context-aware vectors, obtain the values for the potential next words in our sequence, convert these values to obtain probabilities, and then finally derive our next word. But let's take a step back and remind ourselves first what our primary goal is here, which for LLMs is to predict the next word in the sequence. In our case, our input is the book Rabbit Run was written by which author, to which our next word that's predicted will be John. Then we continue this process but append John to the end of our initial input, and as such get the next word, which is update. We can continue this process indefinitely to generate new words in our sequence, which is what makes LLMs autoregressive, meaning the model generates one token, or word in this case, at a time, using the words that are already produced as input for the next prediction. The final result that we get in our case is John Updike as our answer. So given that this is our goal input, a question becomes, what is the output space here? That is, if we're trying to predict the next word, what are our options to select from? Well, for simplicity case, we can consider the English dictionary, which has around 170 to 200,000 words in it. This means that the words we have to choose from in our output space is any word within this 170 to 200,000 words, where in this case, we would select the word John as our next word. Now that we have this overarching goal in mind and an idea of our output space, let's go back to the output from our transformer block, which is a set of context-aware vectors, one for each word in our input sequence. We take these vectors and we process them through our output layer. If we consider just a single vector, say for the word the in our input, and we run it through our output layer, we then get 170 to 200,000 logits or values, one for each potential word in our output space, where each value in this outcome vector represents how strongly the model thinks that our particular word should be the next word, with a higher value meaning it believes more strongly in it being the next word. We can naturally turn these into probabilities, where now each probability represents the likelihood of the given word in the output space being the next word after our word the. We can sample the space to get probabilistic outcomes of the next word, or we can pick the most likely one. In this case, the most likely one would be book. We can then do this for each word in our sequence. However, looking back at our contextualized vectors, given that the output of our output layer gives us the likelihoods of the next word, the only vector in our context-aware vectors that we really care about is our last vector, which represents the last word in our sequence. Then if we go through this process again with our last vector author, we get the next word in our sequence and the first word in our answer, which is John. So to summarize our final output stage, we start with our context-aware vectors, obtain the values associated with each potential next word, convert them into probabilities, and then select our next word. And we do this over and over again. So with regards to the overall process, we first begin with raw text and convert them into vector representations. Then we inject the contextual information in them via our transformer blocks. Then obtain the likelihood and selected our next word. In summary, in this video we went through an overarching LLM architecture. We discussed the three general stages associated with this process and went through an iterative example. In the next video, we'll dive deeper into detail into how each one of these stages and substages works, starting with the input representation stage. In particular, although we have used words in this video for our example, we'll delve deeper into how text tokenization works and what tokens actually mean. Thank you for watching. Please like and subscribe if you found this helpful, and consider following and supporting us on all platforms.